This microscope footage shows a liquid crystal cell, a cluster of molecules shifting and twisting in an organized rhythm that mimics tiger stripes. A normal crystal, like salt or diamond, repeats its atomic structure across space. This material suggests a stranger possibility. Matter can also organize itself across the dimension of time. Our intuition suggests that crystals are rigid solids, that constant motion always requires a motor, and that repeating patterns in time are merely forced oscillations, like a swinging pendulum. These assumptions align with the macroscopic physics of our everyday lives, where motion usually requires an external push and eventually loses energy. But inside this liquid crystal cell, those rules fail. Understanding this motion requires a new definition of what a crystal actually is. In ordinary physics, the laws of nature are constant. A system operating at 8:59 obeys the exact same physical laws at 9 o'clock. In this state, time is a smooth, continuous background. Space works the same way. In an empty void, every position is equal. But when atoms form a standard crystal, they select fixed, repeating positions. They break the symmetry of space. A mathematical no-go theorem long suggested time crystals were impossible. Proving a system at rest in thermal equilibrium cannot spontaneously develop a repeating cycle. The loophole is non-equilibrium matter. Continuously driven by energy, it breaks time symmetry and develops its own spontaneous rhythm. This state of matter organizes its own structural lattice across the dimension of time. In 2025, University of Colorado Boulder researchers moved this concept into a visible material. They achieved a continuous space-time crystal using steady, unstructured light. They used a nematic liquid crystal of rod-like molecules. Exposed to light, these reorganize into twisting topological solitons. Mathematically, a standard crystal's density pattern perfectly overlaps when shifted by lattice unit A. Similarly, a time crystal's measurable property perfectly repeats after a specific time interval, tau. A space-time crystal combines these variables. Its observable state repeats across both its physical position and its position in time. These moving stripes are the visual manifestation of topological solitons locking into a strict mathematical grid of space and time. To prove this is a new phase of matter, scientists must distinguish it from a simple wave pattern stirred up by the light. In physics, a genuine phase of matter is defined by collective stability. While a simple wave dissipates when nudged, a crystal structure is the preferred state of the system. Therefore, the rhythm must persist even when the environment introduces physical disturbances. A swinging pendulum eventually loses energy and decays. A speaker cone simply follows the external signal fed into it. Because the liquid crystal maintains this specific rhythm against perturbations, it qualifies as a distinct, ordered phase of matter. This phase requires steady light to exist and creates no free energy. It is a state of matter, not a source of power. Liquid crystals flow like liquids, but preserve orientational order, bridging the gap between familiar materials and the non-equilibrium phases usually reserved for quantum physics. Redefining order means moving past the idea that crystals must be hard objects. Soft matter can obey the same complex organizational rules. The Boulder experiment pulled time crystals out of the invisible quantum realm of trapped ions and into a material we can see through a microscope. This stability could be used in quantum simulators, in next-generation displays, and anti-counterfeiting designs that are mathematically impossible to forge. Physicists are now mapping the precise mathematical boundaries that separate this genuine crystalline order from everyday fluid patterns and convection. An ordinary crystal's order is dictated by where its pattern repeats. The space-time crystal proves matter can also dictate when it returns.